Good evening, and welcome to The Sleepy Scientist, a calm corner of the internet where curiosity drifts slowly, like mist over still water. If you're settling down for the night, this is your time to unwind, breathe, and let your thoughts soften. Tonight, we'll be exploring the chemistry of the invisible, a quiet journey through the unseen forces that shape the world around you. From the air you breathe to the water you drink, from the scent of rain to the warmth that lingers in sunlight, chemistry is always at work, even when it hides in plain sight. Before we begin, I'd love to know, where are you watching or listening from tonight? It always fascinates me to see just how far these gentle pockets of curiosity reach across the world. If you enjoy these calm explorations, a gentle like and subscribe would mean a lot. It helps this little community of sleepy scientists grow. And if you're already subscribed, thank you sincerely for being part of it. Just make sure you've clicked that small notification bell so you won't miss the next quiet adventure through science and sleep. And, well, I hope tonight's topic isn't too interesting that it keeps you awake. But if it does, at least you'll drift off knowing a little more about the invisible world quietly working all around you. So, what really lies beyond what we can see? And how much of life's chemistry depends on things that never meet the eye? The world feels solid, bright, and complete, full of colour, texture, and sound. Yet the truth is, almost everything that governs it is invisible. Chemistry thrives below the threshold of perception, shaping every breath, every drop of water, every quiet flicker of light. What we see, smell, and feel is only a thin surface of reality, painted over a vast and hidden structure of molecules and motion. Human senses are remarkable, but also profoundly limited. The eyes, for example, only perceive a narrow strip of light between roughly 380 and 740 nanometers in wavelength, a tiny slice of the electromagnetic spectrum. Everything beyond that range, from ultraviolet light to infrared heat, passes by unnoticed. Bees, snakes, and countless other creatures live in richer spectra, while we navigate the world through a modest window of colour. The nose, though astonishing in its sensitivity, also has boundaries. It can detect certain compounds at concentrations of just a few parts per billion, an invisible wisp of matter that can fill a room with scent. Yet many molecules, even reactive or abundant ones, never register at all. Oxygen, for example, is completely odourless, though it fills every breath and sustains every heartbeat. The sense of touch fares no better. It can feel the smoothness of a glass surface or the coarseness of sand, but it cannot trace the vibration of a single molecule or the hum of atoms locked in crystal lattices. The human body is tuned for comfort, not for microscopic truth. This limitation creates an illusion, the illusion of emptiness. Hold your hand in the air and it feels like nothing is there, but space is thick with nitrogen, oxygen, argon, carbon dioxide, and water vapor molecules bouncing, colliding, and spinning at hundreds of meters per second. Their motion generates pressure, temperature, and weather, yet all of it happens unseen. The stillness we perceive is only a trick of scale. Transparency is another form of invisibility. When light passes through a substance rather than being absorbed or scattered, that substance appears clear. The difference between a cloud and a pane of glass, for example, lies not in their composition, but in the way they interact with light. Tiny droplets in a cloud scatter light in all directions, making it white and opaque. In glass, the atomic arrangement allows most visible light to pass straight through, leaving only a faint reflection behind. The physics of visibility comes down to absorption, transmission, and scattering, the quiet negotiations between light waves and matter. Even substances we think of as colourless are often selective in their transparency. Pure water, if you look through enough of it, is faintly blue because it absorbs red wavelengths more efficiently. Air itself, though seemingly clear, scatters shorter blue wavelengths more than red, which is why the sky glows cerulean by day and softens to amber at sunset. The colour of the world is a product of scattering on a planetary scale, but not all invisibility is optical. Some of it lies in concentration. A few molecules of dye dropped into a vast lake vanish from sight, not because they disappear, but because they become hopelessly outnumbered. The human eye needs a certain density of pigment before colour registers. Similarly, a single puff of perfume can fill a room with scent, but as it spreads and dilutes, its signal fades below detection even though the molecules remain in motion. This is chemical invisibility, not absence, but dilution beyond awareness. In the laboratory, chemists speak in parts per million, or parts per billion, measuring what can't be seen but still exists. For comparison, 1 part per billion is like a single grain of sand hidden among 1,000 metric tons of beach. Many environmental processes happen at those whisper-thin scales. Ozone in the upper atmosphere, trace metals in seawater, or hormones circulating in the bloodstream. Each one is invisible, yet essential. There's also a slower kind of invisibility, the kind that belongs to time. Some chemical reactions unfold over centuries, making them imperceptible to the impatient human eye. Iron rusting in a forgotten shed, limestone dissolving in gentle rain, or the slow decay of organic matter into soil. Each is a transformation so gradual it seems static. Yet if time were sped up, the world would appear to breathe. Metals fading, rocks melting, oceans shifting in colour as invisible reactions ripple through them. Kinetic invisibility hides motion not by smallness, but by slowness. When we describe something as inert or still, we're usually describing our own limits of observation. Even a stone resting on a windowsill vibrates on an atomic scale. Its bonds stretch and compress in trillionths of a second, trading energy with the air. The atoms within it exchange tiny quanta of motion with every passing vibration of light or sound. To call it lifeless is a kind of poetic error, a human shortcut for a dance too subtle to see. If our eyes could see carbon dioxide, dinner conversations would look like ghost clouds, swirling across the table with every breath and laugh. Invisible chemistry is the stagehand behind every visible act. It carries heat away from a cooling cup of tea, releases aromas from food, and powers the quiet corrosion of metal and stone. It is everywhere, doing everything, all the time. What we call nothing is rarely empty. Even the clearest air and purest glass are bustling with unseen structure and motion. Light bends as it passes through them, atoms shift and vibrate, and molecules exchange energy in constant, silent dialogue. The visible world is just the faint outer edge of a much larger story. To understand invisibility in chemistry is to accept that most of reality happens beyond our senses, not out of reach, but beyond what our bodies were built to notice. The unseen world doesn't need to be dramatic to be powerful. It's enough to know that when you look through a window or breathe in or rest your hand on a surface, an intricate, invisible conversation is already taking place, shaping your world with a patience that never asks to be seen. Air feels like nothing at all. You can wave your hand through it, walk through it, even fall through it, and it gives no resistance. Yet this seeming emptiness is one of the most intricate and finely balanced chemical mixtures on Earth. Every breath, every cloud, and every whisper of wind is built from it. Invisible, yes, but never idle. If you could slow the world to the scale of molecules, the air would look like a crowded ballroom. Billions upon billions of dancers, all moving at hundreds of meters per second, collide and rebound in endless motion. Each molecule carries its own rhythm, some fast and light, some slow and heavy, and together they make the atmosphere hum with quiet energy. Despite its complexity, air's main ingredients are simple. Roughly 78% of it is nitrogen, 21% is oxygen, just under 1% is argon, and about 0.04% is carbon dioxide. The rest, a delicate sprinkling of trace gases like neon, helium, methane, and ozone, make up the finishing notes of this invisible symphony. That tiny fraction of carbon dioxide, although small enough to be written as a decimal, helps warm the planet, feeds plants through photosynthesis, and fuels the slow cycles that have kept life in balance for billions of years. To chemists, these numbers describe a masterpiece of proportion. Nitrogen, the quiet majority, dominates the stage. It is stable, unreactive, and content to stay as it is. Each nitrogen molecule consists of two atoms bound together by one of the strongest triple bonds in nature. That bond makes nitrogen a patient observer in the atmosphere. It rarely joins in the chemical drama, yet life depends on breaking it. Certain bacteria, lightning strikes, and industrial processes can split nitrogen apart, fixing it into compounds like ammonia and nitrates that plants use to build proteins. Without this rare act of molecular generosity, ecosystems would starve. So while nitrogen mostly stands still, it holds the keys to life's supply chain. Oxygen, on the other hand, is the extrovert of the group. Energetic and social, it eagerly reacts with other elements, driving combustion, respiration, and countless oxidation reactions. When oxygen meets fuel, whether in a candle flame or inside your cells, it releases energy by forming stable bonds with carbon and hydrogen. Every breath you take carries oxygen inward to be traded for carbon dioxide, the byproduct of that invisible exchange. The air you exhale is about 4% carbon dioxide and much warmer and wetter than when it entered your lungs. Argon, the next most common gas, is the true wallflower of the ballroom. It belongs to the noble gases, chemically inert and content to float through the atmosphere without forming bonds. Argon atoms drift silently through every breath you take, unchanged since the earth first cooled. The air in your lungs tonight almost certainly contains argon that once passed through the lungs of ancient creatures, or even the chambers of long-extinguished volcanoes. Argon never ages, it merely moves. Carbon dioxide, though present in minute amounts, plays a role far beyond its share. Plants absorb it and transform it into sugars, animals exhale it, and oceans act as vast carbon reservoirs. It's transparent to visible light, but absorbs infrared radiation, which helps warm the planet's surface. The entire climate depends on the invisible tug-of-war of this delicate molecule. Too little, and the planet freezes. Too much, and it overheats. Yet carbon dioxide doesn't act alone. It partners with water vapor, another invisible but crucial player. Water vapor is the atmosphere's shapeshifter, appearing and vanishing with temperature and pressure. It makes up anywhere from 0 to 4% of the air, depending on humidity. Unlike nitrogen or oxygen, it constantly changes phase, evaporating, condensing, forming clouds, and raining out again. When warm air rises and cools, water vapor condenses into tiny droplets, releasing latent heat that drives weather systems. Even when no clouds form, water vapor affects how warm or cool the air feels against your skin. It cushions temperature swings, softens dry air, and creates the dew that glistens on grass at dawn. Humidity, though often described in forecasts, is pure chemistry in motion. It is the measure of how many water molecules float among the nitrogen and oxygen ones. A humid night feels heavy not because the air is thicker, it barely changes in density, but because water molecules absorb and hold heat more effectively, slowing the cooling of the air and of your body. That same property is what makes humidifiers, fog and mist so comforting in dry conditions. Dalton's law, a simple but profound principle of chemistry, explains how all these gases coexist peacefully. Each gas in a mixture exerts its own partial pressure, behaving as though it alone occupied the entire volume. The total pressure of the atmosphere, about 101 kilopascals at sea level, is just the sum of all their tiny contributions. It's as if every gas pays its rent independently, yet all share the same space in harmony. That balance allows us to breathe comfortably, cook food, inflate balloons, and launch airplanes without the atmosphere favouring one molecule over another. Even the air inside a room is dynamic. As you breathe, exhale, and move, you constantly change its composition. The breath you release contains water vapour, carbon dioxide, and trace compounds like acetone and ethanol, products of metabolism. These molecules quickly disperse through diffusion, mixing invisibly with the surrounding air. When sunlight shines through a window, you can sometimes see dust motes drifting in a beam of light. But those particles, tiny as they are enormous compared to the gases moving around them. The true motion of air is hidden, soundless, colourless, ceaseless. Despite being invisible, air has weight. A column of it stretching from the ground to the edge of space above every square metre of the Earth's surface weighs about 10 metric tons. That enormous unseen weight presses down equally in all directions, giving us atmospheric pressure. Without that pressure, water would boil away at room temperature and life would lose its delicate balance. The air's constant push keeps liquids stable, our lungs functional, and weather systems alive. Every so often, the chemistry of the atmosphere reveals itself through scent or sensation. The sharp tang before a thunderstorm comes from ozone and nitrogen oxides created by lightning. The earthy freshness after rain, called petrichor, arises from oils released by soil microbes and carried upward by tiny air bubbles bursting from wet ground. Even the smell of the sea comes from invisible sulfur compounds drifting off waves. Each aroma is a molecular announcement, proof that air is never empty, only subtle. Imagine it again as that vast ballroom of molecules, nitrogen keeping order, oxygen whirling energetically, water vapour weaving between dancers, and argon watching from the sidelines. The temperature, pressure and humidity set the rhythm, and sunlight occasionally steps in as the conductor. It's a quiet performance, but one that never ends. So while air might feel like nothing, it is in truth everything, an invisible architecture holding up weather, breath and life itself. Every inhale draws in a small portion of that grand chemical equilibrium, linking you to forests, oceans, and every living thing that has ever breathed before. The next time you sigh or feel a breeze against your skin, remember that what feels like emptiness is really a universe of molecules whispering in perfect balance. Water has a reputation for simplicity, but that's only because it hides its genius so well. It looks clear, feels soft, and seems harmless enough, yet it is the quiet architect of life and one of the strangest liquids in the universe. Every drop of water is full of invisible structure, tiny electric fields, shifting bonds and delicate balances that make it behave less like a passive fluid and more like a conductor of secrets. The magic begins with the shape of the water molecule itself. 2 hydrogen atoms and 1 oxygen atom form a bent asymmetrical structure, like a little boomerang of charge. The oxygen end pulls electrons toward itself, making it slightly negative, while the hydrogen ends become slightly positive. This uneven distribution of charge is called a dipole, and it gives water polarity. Each molecule behaves like a tiny magnet, with opposite poles that attract and repel its neighbours. billions upon billions of these molecules cling to one another through a type of weak electrostatic attraction known as hydrogen bonding. It's a soft, flexible bond, constantly breaking and reforming, giving water its flowing nature and high cohesion. This polarity is also why water can dissolve so many substances. When an ionic compound such as salt is dropped into water, the positively charged sodium and negatively charged chloride ions are immediately surrounded by water molecules that align according to charge. Oxygen atoms point towards sodium, hydrogen atoms point toward chloride, forming little cages of stabilization called hydration shells. The lattice of salt crystals falls apart, not by force, but by persuasion. Water's dipoles coax ions into the solution, wrapping them so securely that they stay separated and dispersed. To the naked eye, the salt simply disappears, but in truth, it's still there, floating as a dance of ions held in watery suspension. These free ions are what make water conductive. Pure water, stripped of impurities, is actually a very poor conductor of electricity. But in the real world, water is never truly pure. It picks up ions from the air, from the ground, and from whatever it touches. These ions, sodium, calcium, magnesium, and countless others, act as invisible couriers of charge, allowing electric current to pass through. That's why distilled water is safe to touch with electricity, but seawater, rich in dissolved salts, can deliver quite a shock. Electrolytes, those charged particles, are also vital inside the human body. They allow nerves to fire, muscles to contract, and hearts to beat, all thanks to chemistry that remains hidden within clear liquid. Even water itself can create ions, though in exceedingly small amounts. A few molecules constantly split into hydrogen ions and hydroxide ions in a process called autoionization. The balance between these two ions determines water's pH, a measure of how acidic or basic a solution is. A perfectly balanced solution has a hydrogen ion concentration of 1 part in 10 million, which corresponds to a pH of 7. On this logarithmic scale, each whole number represents a 10-fold change in acidity. A pH of 6 is 10 times more acidic than neutral water, while a pH of 8 is 10 times more basic. It's a subtle system, but an incredibly important one. Living organisms rely on a stable pH for their biochemistry to function correctly. Enzymes, for instance, are exquisitely sensitive to acidity. A small shift can change their shape and render them ineffective. Your blood, for example, must stay within a pH window of about 7.4. Drift too far from that, and life itself begins to falter. Thankfully, water has a quiet ally that keeps things stable: buffers. A buffer is nature's polite way of saying, let's not overreact. It is a mixture of a weak acid and its corresponding base that resists sudden changes in pH. When extra hydrogen ions enter the system, the base component gently absorbs them. When hydroxide ions appear, the acid part donates a proton to restore balance. The overall effect is calm, predictable chemistry, even when the world outside is chaotic. One of the most elegant examples of buffering happens in your own body. The bicarbonate system in the blood uses carbonic acid and bicarbonate ions to keep pH steady. When you hold your breath, carbon dioxide builds up, forming more carbonic acid, which would make the blood more acidic. To counter this, the body increases breathing rate once you exhale again, releasing the carbon dioxide and restoring balance. You could think of it as an invisible chemical conversation, breath negotiating with blood. Another crucial buffering system operates in the ocean. The vast blue expanses that cover most of the planet act as both a sink and a stabilizer for carbon dioxide. When carbon dioxide dissolves in seawater, it reacts to form carbonic acid, which can then split into bicarbonate and carbonate ions. This trio of compounds creates a natural buffering network that prevents dramatic shifts in ocean pH. Without it, marine life with shells or skeletons made of calcium carbonate would dissolve in their own habitat. Ocean buffering has quietly protected life for hundreds of millions of years, though it is now being tested by rising levels of atmospheric carbon dioxide. Buffers work on smaller everyday scales as well. Your saliva, for instance, contains bicarbonate ions that neutralize acidity after meals, protecting tooth enamel from damage. Even swimming pools rely on buffering systems to stay comfortable and safe. The addition of weak acid and base pairs prevents wild swings in pH that could otherwise make the water corrosive or irritate skin. Everywhere water appears in chemistry or in life, it carries with it this invisible sense of balance. The duality of water, its ability to dissolve, to ionize, to stabilize, is what makes it the universal solvent. It's both reactive and gentle, able to host some of the most energetic reactions known to science while remaining peaceful enough to bathe in. It can carve canyons over centuries, yet cradle delicate living cells without harm. And through all of this, it never loses its calm transparency. What we call clear is in fact endlessly active. Every glass of water you see is a scene of constant negotiation. Molecules jostle, ions drift, hydrogen bonds flicker on and off, and the pH stays steady through silent teamwork. If you could watch it happen, you'd see colourless fireworks, energy trading hands in microscopic bursts. The stillness of water is an illusion. Beneath its surface, chemistry never stops. So the next time you pour a glass of water, remember that you're holding a tiny miracle. It's not just a drink, but a chemical masterpiece. Polarity, ions, and balance all working in unison. A fluid so familiar it feels ordinary, yet so complex it humbles even scientists. Water doesn't just reveal chemistry, it embodies it, quietly teaching that stability and motion can coexist, and that calmness itself can be a form of power. If you drop a little ink into a glass of still water and watch closely, you'll see a slow and graceful ballet. The colour begins as a concentrated swirl, then curls outward, thinning and fading until the whole glass takes on a faint tint. No stirring, no breeze, just motion arising from stillness. That is diffusion, chemistry's quiet choreography, the patient process that keeps the universe from ever truly standing still. To understand diffusion, it helps to start with something even smaller, Brownian motion. In 1827, the Scottish botanist Robert Brown looked through a microscope at pollen grains floating in water and noticed something strange. The grains were jiggling in place, constantly twitching and dancing, even though the water around them seemed perfectly calm. Brown suspected life might be causing the motion, but when he repeated the experiment with particles of dust, the dancing continued. Life, it turned out, had nothing to do with it. Decades later, in 1908, Albert Einstein provided the explanation. Each pollen grain, he realized, was being bombarded from all sides by the water molecules around it. Water may look still, but its molecules move at hundreds of meters per second, colliding and rebounding like invisible billiard balls. Those countless tiny impacts push and pull the pollen in random directions. The result is a visible, jittery motion that never stops. This random jostling, Brownian motion, was the first tangible proof that atoms and molecules exist, a quiet triumph of observation over invisibility. Diffusion is the same dance viewed on a larger scale. It's the tendency of particles to wander from areas where they are crowded to areas where they are sparse, simply because they are always moving and bumping into one another. Over time, these random steps lead to an even spread of concentration. The ink in the glass, the smell of bread wafting through a kitchen, the warmth from a cup of tea fading into the air. All of them are governed by the same law of gentle dispersal. If you were small enough to ride on one of those ink molecules, diffusion would feel like chaos. You'd be knocked about in every direction, buffeted by collisions, zigzagging endlessly. But when billions of molecules move this way, their collective motion forms a predictable pattern. Chemists describe this with fixed laws of diffusion, which simply say that particles move down their concentration gradient. The crowded regions push molecules into the emptier ones until everything evens out. It's a statistical certainty born from randomness. The pace of diffusion depends on temperature. As heat rises, molecules move faster, collide more often, and mix more quickly. Cold slows everything down. That's why a sugar cube dissolves sluggishly in iced tea, but vanishes in moments in a hot drink. Temperature isn't just warmth, it's motion made invisible. Each degree is an increase in the restless energy of atoms, a faster hum in the background of matter. Diffusion happens everywhere, all the time. In your lungs, oxygen diffuses through the delicate walls of tiny air sacs into your blood, while carbon dioxide slips the other way. In leaves, carbon dioxide diffuses inward for photosynthesis, while oxygen drifts outward to the open air. Even smells rely on diffusion. When someone opens a jar of coffee, its aroma molecules spread outward, colliding their way through air molecules until the whole room fills with the scent. It feels like magic, but it's pure mathematics and motion. In the kitchen, diffusion is the unseen artist behind flavour. As soup simmers, ingredients release compounds that wander and mingle through the liquid, building complexity. The same process softens fruit in sugar syrup, balances salt through a brine, and spreads aroma from a pot of tea. Nothing is static in a kitchen, not even the air. Diffusion blurs boundaries, turns edges into gradients, and allows flavour to reach equilibrium. The process also underlies the spread of heat. When you hold a mug of hot chocolate, warmth diffuses through the air and into your hands. At the atomic level, faster-moving molecules bump into slower ones, transferring energy bit by bit until everything around you settles into the same gentle temperature. It's why a cold room warms slowly after you light a fire. Energy seeps outward through collisions, spreading itself evenly, quietly fulfilling nature's love of balance. The human brain even benefits from diffusion on a microscopic level. Within every neuron, ions drift through channels to carry electrical signals, while neurotransmitters diffuse across tiny gaps to relay messages between cells. The thoughts you're having right now about ink, air, and motion are being powered by diffusion happening at the speed of molecules. Even memory is, in part, a diffusion of chemistry and motion. Einstein's theory of Brownian motion did more than explain a botanical curiosity. It offered a way to measure the size of atoms, to estimate Avogadro's number, and to bridge the gap between the invisible and the calculable. 100 years later, scientists still use Brownian motion to study nanoparticles, viruses, and suspended colloids. The same restless movement that made pollen dance now helps us understand everything from pollution to protein folding. There's also poetry in it. Diffusion is patience embodied. It doesn't rush, doesn't force, doesn't demand. It simply allows time and motion to do their work. No matter how still the world seems, balance is always being restored in silence. The ink in the glass will keep spreading until every molecule has explored every corner available to it, guided by nothing but randomness and inevitability. It's comforting in a way. Even in stillness there is progress. Even in quiet there is change. The same principle that softens the air around you smooths the boundaries of galaxies and distributes starlight across the cosmos. Diffusion is one of nature's simplest ideas. Things move until they're balanced, but it's also one of its most universal. So the next time you see steam curl from a cup, or scent drift through a room, or colour fade gently through water, Imagine it as the planet's softest kind of movement. Molecules meandering without plan, achieving harmony through time. Like thought spreading in the mind, diffusion leaves no trace of its path, only the calm it brings when everything has quietly found its place. The universe, for all its chaos, has a deep love of balance. Push it in one direction, and it will quietly lean back the other way, adjusting, compensating, and settling into a new harmony. In chemistry, this gentle conversation between forces is called equilibrium. It isn't a frozen moment of stillness. It's an ongoing negotiation, a continuous tug-of-war where both sides are evenly matched and never rest. Every chemical reaction, no matter how simple, has two directions, a forward path and a reverse path. In the forward direction, reactants combine to form products. In the reverse, those products can break apart or recombine to recreate the original reactants. At first, the forward reaction might dominate, building new molecules with enthusiasm. But as the products accumulate, some begin to drift backward, undoing the progress. Over time, the rates of both reactions balance out. Molecules continue to change sides, but the overall composition remains constant. That moment, where everything moves, yet nothing changes, is chemical equilibrium. The idea can sound abstract until you realize it's happening everywhere. The air above a soda bottle is in equilibrium with the fizz below it. Carbon dioxide dissolves into the liquid and escapes back into the air at equal rates. The hiss when you open the bottle simply breaks that equilibrium, lowering the pressure and allowing more gas to leave than can return. The bubbles that rise and burst are not a sign of chaos, but of a new balance being sought, a temporary imbalance correcting itself. Chemistry doesn't like extremes. It prefers compromise, and one of its most elegant rules explains exactly how this compromise unfolds. It's called Le Chatelier's principle, and it states that when a system at equilibrium is disturbed, it will adjust itself to minimize the disturbance. In other words, when life, or the universe, changes the rules, chemistry quietly rearranges the pieces to restore calm. A familiar example hides in your bloodstream. Hemoglobin, the molecule that carries oxygen in red blood cells, binds oxygen where concentrations are high, like in the lungs, and releases it where concentrations are low, like in muscles that are using oxygen for energy. This happens because hemoglobin's affinity for oxygen changes with its environment. When there's too much carbon dioxide or the pH drops, the equilibrium shifts to release oxygen. When carbon dioxide levels fall again, the balance reverses and oxygen is picked up once more. Every breath you take depends on these reversible reactions, the constant give and take between binding and releasing, holding and letting go. Even the oceans perform this balancing act. When carbon dioxide dissolves in seawater, it reacts to form carbonic acid, which can then break apart into bicarbonate and carbonate ions. These reversible reactions create a vast buffering system that regulates the ocean's acidity. If more carbon dioxide enters the water, some of it stays dissolved, while the rest is converted into other forms, minimizing sudden shifts in pH. Without this hidden dance of equilibrium, marine life with delicate shells made of calcium carbonate would not survive. The same principle governs much smaller everyday moments. When you breathe into a glass of water through a straw, carbon dioxide dissolves and forms carbonic acid, slightly lowering the pH. Leave it sitting, and the reverse happens. The gas slowly escapes, restoring the balance. Or think of ammonia in a household cleaner. If you open the bottle, the pungent smell fills the air because gaseous ammonia escapes from its equilibrium in solution. Close the lid, and it slowly redissolves. These are small reminders that even ordinary life is built upon reversible reactions. Chemists describe equilibrium using a single value known as the equilibrium constant, or K. It expresses the ratio between products and reactants when the reaction has reached balance. A large value of K means the products are favoured. The forward reaction wins the quiet tug of war. A small value means the reverse reaction dominates, and the reactants prefer to remain as they are. These constants may seem like abstract numbers, but they steer vast processes, from the formation of clouds to the chemistry of metabolism. They are the invisible rules that decide which side of a molecular conversation speaks louder. One of the most beautiful things about equilibrium is that it gives chemistry a kind of patience. Imagine two opposing crowds on a suspension bridge, evenly matched in strength, each pulling in opposite directions. The bridge doesn't collapse or swing wildly. Instead, it hangs in perfect tension. That tension, invisible yet constant, is what holds the chemical world together. It's not a stalemate, it's harmony in motion. Temperature and pressure can tip that harmony. Warm a system and it may shift toward reactions that absorb heat. Cool it, and it will lean toward those that release it. That's why dissolving a solid in warm water often happens faster and more completely. The equilibrium adjusts to use the added energy. Compress a gas mixture, and the balance will favour reactions that produce fewer gas molecules relieving the pressure. These adjustments happen smoothly, instinctively, like nature exhaling after a long breath. In the atmosphere, equilibrium keeps gases distributed in delicate proportions. Carbon dioxide and oxygen exchange between air, water, and living things, maintaining the cycle of respiration and photosynthesis. Plants pull carbon dioxide from the air and release oxygen. Animals do the opposite. The balance doesn't remain perfectly still, but it hovers around a state of mutual support. The air you exhale may become part of a leaf's photosynthesis within days, completing the invisible circle. Even solid materials exhibit their own form of equilibrium. Iron exposed to air forms rust, a slow conversion of metal into oxides. The surface of the metal continuously reacts with oxygen and water, forming a layer that can, under the right conditions, slow further corrosion. That protective crust is a kind of local equilibrium, an armistice between metal and air. In other cases, like tarnish on silver, the reaction continues until the system finds its quiet point, the state where chemical desire finally rests. There is a comfort in knowing that everything seeks balance. Whether in a teacup, an ocean, or the bloodstream, nature dislikes being out of tune. Push a reaction too far, and it gently pushes back. Disturb a balance, and chemistry will find a way to restore it. This principle doesn't just keep the world stable, it makes it resilient. It's why ecosystems recover, why our bodies maintain homeostasis, and why life can persist through constant change. Equilibrium isn't stillness, it's motion perfectly balanced. Molecules keep moving, exchanging partners, trading energy, and shifting positions, yet the overall composition holds steady. It's like watching a crowd where everyone is walking in different directions, but from a distance the scene looks peaceful and unmoving. The appearance of calm hides 1,000 tiny negotiations happening every second. If you ever need a reminder that stability doesn't mean stagnation, look to chemistry. The world isn't calm because it stopped moving. It's calm because everything is moving just enough in both directions. In that quiet tug-of-war between change and constancy lies the secret of endurance, the art of staying the same by never truly being still. Every chemical reaction has a story to tell, but some unfold quickly and others take their time. A match bursts into flame in an instant, yet iron rusts so slowly it feels almost eternal. The difference lies not in the desire of atoms to react. They're always eager for new arrangements, but in the barriers they must cross to do so. Chemistry is full of potential romances that never quite happen because the partners can't find the energy to meet. At the heart of every reaction is a landscape of energy. Imagine two valleys separated by a hill. The reactants begin in one valley and the products wait in the other, but to move from one to the other, molecules must climb the hill in between. That hill represents the activation energy, the minimum amount of energy required to make the reaction go. Only those molecules moving fast enough or colliding with the right orientation can reach the top and roll down the other side. Everyone else just bounces off, waiting for another chance. This is why temperature has such a powerful influence on chemistry. Heat's motion, molecules vibrating, tumbling and spinning more rapidly. As the temperature rises, more and more molecules have enough energy to cross that barrier. Reaction rates don't just increase steadily, they often grow exponentially with temperature. The relationship was formalized in the early 20th century by Svante Arrhenius, whose equation linked rate and temperature in a simple, elegant curve. Each degree of warmth adds a little more motion to the molecular world, nudging more collisions into success. You can see this principle everywhere. Bread dough rises faster in a warm kitchen because yeast enzymes work more quickly when heated. Milk spoils sooner on a summer day for the same reason. The microbe's chemistry accelerates. Even metal corrodes faster in heat because more energetic atoms swap electrons and bonds more readily. Cold, by contrast, slows the dance. Refrigeration is just the art of making chemistry drowsy. Still, not all reactions are content to wait for warmth. Many proceed sluggishly even under ideal conditions because their activation energy is too high. That's where catalysts come in, chemistry's quiet facilitators. A catalyst doesn't change the starting or ending point of a reaction, nor does it supply energy from outside. It simply provides an easier path, lowering the hill between the valleys. A catalyst is like opening an extra door in a quiet hallway. The molecules still move from one side to the other, but they no longer have to climb the stairs to do it. Catalysts achieve this by stabilizing intermediate states, bending the energy landscape into smoother shapes. They might hold reactants in the perfect position for bonding, or briefly form a temporary compound that's easier to rearrange. When the reaction is done, the catalyst is released unchanged, ready to guide another set of molecules. That's the truly magical part. It works tirelessly, accelerating reactions again and again without wearing out. Nature, as always, perfected the technique long before humans noticed. Inside every cell, vast armies of catalysts called enzymes orchestrate life's chemistry with astonishing precision. Each enzyme has a unique shape that fits its target molecule like a key into a lock. When the substrate nestles into its active site, the enzyme bends it, stretches it, and weakens specific bonds until the reaction happens effortlessly. In many cases, the enzyme adjusts its shape to fit even better, what biochemists call induced fit. It's less like a rigid lock and more like a handshake that adjusts until it feels just right. These biological catalysts are breathtakingly efficient. A single molecule of the enzyme catalyst can decompose millions of hydrogen peroxide molecules every second. Without enzymes, digestion, respiration, and DNA replication would crawl at glacial speeds. The chemistry of life would simply not keep up with life itself. Enzymes turn impossible timescales into manageable moments, ensuring that every heartbeat, breath, and thought occurs right on schedule. Humans, eager students of nature, have learned to make their own catalysts for industry. One of the most famous is the Haber-Bosch process, developed in the early 20th century, which uses an iron-based catalyst to combine nitrogen and hydrogen into ammonia. That single reaction underpins modern agriculture, providing the nitrogen fertilizers that feed billions of people. The chemistry itself is simple. Nitrogen plus hydrogen yields ammonia. But without the catalyst, the triple bond in nitrogen gas is too strong to break efficiently. With the catalyst's help, it becomes not just possible, but practical. Catalysts also clean the air we breathe. In the exhaust systems of cars, catalytic converters use metals like platinum, palladium and rhodium to transform toxic gases such as carbon monoxide and nitrogen oxides into less harmful compounds. Each metal surface acts as a stage where molecules land, rearrange and depart as cleaner products. The process happens continuously, quietly and invisibly, an ongoing negotiation between fuel, air and chemistry that makes modern transport tolerable. In the food industry, catalysts perform their work in subtler ways. Nickel or platinum catalysts help hydrogenate oils, turning liquid fats into semi-solid forms used in spreads and pastries. Other catalysts refine fuels, produce plastics, and even aid in creating pharmaceuticals. In almost every product that touches modern life, there's a hint of catalytic craftsmanship behind the scenes. Yet for all their usefulness, catalysts obey the same natural laws as everything else. They can't make an impossible reaction possible. They can only make the possible faster. They don't change the overall balance of energy, only the route taken. A reaction that absorbs heat will still need heat, and one that releases energy will still do so, just with less hesitation along the way. At its heart, kinetics, the study of reaction rates, is about time's role in chemistry. Two reactions might produce the same result, but one might finish in a heartbeat while the other takes centuries. The difference isn't the destination, but the journey, and catalysts are the travel guides of that journey, showing molecules the scenic shortcuts that make the trip smoother. In nature, kinetics and equilibrium coexist like rhythm and melody. One describes the tempo of change, the other the point of balance. Without kinetics, nothing would ever reach equilibrium. Without equilibrium, kinetics would have no final goal. Together they make chemistry dynamic yet dependable, a world in constant motion that still knows where it's headed. There's a quiet comfort in realizing that even the smallest reactions have their own pace, their own patience. A match flares, iron rusts, mountains erode, and stars forge heavier elements, all governed by the same invisible mathematics of motion and energy. Catalysts are simply the caretakers of that motion, easing the way, ensuring that change doesn't have to be rushed or forced, only guided. The next time you see rust forming, bread rising, or a fire burning, you're watching kinetics in action, the slow and fast conversations of atoms negotiating new bonds. Somewhere within those exchanges, catalysts may be whispering directions, helping chemistry find its rhythm. In the quiet, unseen architecture of reactions, they remind us that progress isn't always about effort. Sometimes it's about finding the easiest path through the barrier and then walking it with grace. Light is one of chemistry's most persuasive forces. It carries no mass, makes no sound, and yet it can twist molecules, split bonds, and set entire reactions in motion. Most of its power hides beyond the narrow rainbow visible to human eyes. What we see as colour is only a small window into a vast continuum of energy, stretching from ultraviolet light at one end to infrared and microwaves at the other. To understand light is to understand how energy travels without touch, how photons, those tiny packets of electromagnetic energy, quietly shape both chemistry and life. Every photon carries a specific amount of energy determined by its wavelength. Short wavelengths like ultraviolet have higher energy. Longer ones like infrared or microwaves carry less. The shorter the wavelength, the more capable it is of altering the bonds between atoms. This relationship between wavelength and energy defines the invisible reach of light's chemistry, its ability to build, break, or simply warm. At the high-energy edge sits ultraviolet light, a realm beyond violet in the visible spectrum. Though invisible, its effects are familiar to everyone who has ever had a sunburn. Ultraviolet photons carry enough energy to break chemical bonds, and they do so freely when they reach the skin. The pigment melanin offers some protection, but overexposure can damage DNA, rearrange molecules in skin proteins, and trigger inflammation. The same destructive power, however, also allows light to create. In the upper atmosphere, ultraviolet light strikes oxygen molecules, splitting them into individual atoms. Some of these recombine to form ozone, a molecule of 3 oxygen atoms, that then absorbs more ultraviolet light, preventing most of it from reaching the surface. The result is a delicate shield born from the very energy it deflects. On a gentler note, ultraviolet light is also responsible for something life-sustaining, the formation of vitamin D in the skin. When certain cholesterol-like molecules absorb ultraviolet photons, they transform into precursors of this vital vitamin, which supports bone growth and immune health. In moderation, ultraviolet light both threatens and nurtures, an invisible paradox of destruction and creation. Move a little farther down the spectrum and you arrive in the realm of visible and near-infrared light, the band that nourishes the planet. Here, the energy of photons is tuned perfectly for photosynthesis, the process by which plants capture light and convert it into chemical energy. Chlorophyll molecules absorb mostly red and blue light, reflecting green, which is why leaves appear that colour. Inside each chlorophyll, the absorbed photon excites an electron, lifting it to a higher energy state. That energy then drives a cascade of reactions that ultimately splits water, releases oxygen, and stores the captured sunlight in sugars. Every tree, flower, and blade of grass performs this controlled photochemistry, weaving invisible light into tangible life. The same principle fuels many modern technologies. Solar panels, for instance, mimic photosynthesis in a more direct electronic way. Photons strike semiconductor materials, freeing electrons that flow as electrical current. Artificial photochemistry turns sunlight into electricity, echoing the natural dance that plants perfected billions of years ago. Just beyond the visible lies the infrared region, a spectrum of warmth rather than brightness. We can't see infrared light, but we can feel it as heat radiating from a campfire, a cup of coffee, or the sun-warmed pavement after rain. Infrared light doesn't break bonds. Instead, it makes molecules vibrate. Each chemical bond behaves like a tiny spring between two masses, stretching and bending in rhythm with absorbed infrared frequencies. Every molecule has its own pattern of vibrations, creating a unique spectral fingerprint. Scientists use infrared spectroscopy to identify substances by these vibrations, listening to molecules sing in frequencies too slow for the eye but too quick for the ear. Infrared energy also underpins the greenhouse effect. Molecules such as carbon dioxide, methane, and water vapor absorb and re-emit infrared light, trapping warmth within the atmosphere. Without this invisible retention of heat, Earth would be far too cold to sustain life. The gentle glow of infrared light is, quite literally, the planet's blanket. Soft, subtle, and essential. Even longer wavelengths lead us into the world of microwaves. They carry far less energy per photon, not nearly enough to break or rearrange chemical bonds. But what they lack in intensity, they make up for in rhythm. Microwaves interact with molecules that have electrical dipoles, tiny imbalances of charge like water. When microwaves pass through food, they cause those dipoles to rotate back and forth millions of times per second, generating frictional heat. The process is uniform and quick, warming food from the inside out. You could say microwaves shake dinner molecules until they politely warm up. What feels like modern convenience is really a demonstration of electromagnetic patience. Microwaves rely on resonance, matching their frequency to the natural motion of water molecules. Too high in energy, and bonds would break. Too low, and nothing would happen. The result is an everyday miracle. Energy transferred invisibly, transforming cold leftovers into comfort with no visible flame at all. Light beyond sight doesn't just interact with matter, it reveals it. Each wavelength speaks to the world in its own language. Ultraviolet light probes structure by breaking it. Visible and near-infrared light build it, driving life's chemistry. Infrared light warms and measures it. Microwaves whisper through it. Together they weave a seamless fabric of interaction, energy forever cycling between motion, warmth, and form. There's poetry in the way light moves through the unseen. It slips through air without resistance, scatters in water droplets to create rainbows, and penetrates skin deep enough to trigger the chemistry of life itself. Most of the light that shapes our world never reaches our eyes. It hums quietly in the background, tracing energy exchanges that make the sky blue, keep the oceans liquid, and warm the surface of the planet just enough to bloom. If visible light is the melody of the universe, then ultraviolet, infrared, and microwave light are the harmonies that give it depth. They're reminders that what we perceive is only a fragment of reality's full score. The invisible parts carry most of the energy, most of the warmth, and most of the chemistry. So when you feel the sun on your face or see steam rise from a cup, remember, the light you see is only half the story. Beyond the bright edges of perception, invisible wavelengths are shaping everything, heating, healing, building, and sustaining. Light, in all its unseen forms, is the quiet chemist of the cosmos, forever turning energy into order and warmth into life. Seeing is believing, but in chemistry, belief often begins where sight ends. The naked eye can only follow colour and shape, yet the real action, the bond breaking, the energy swapping, the molecular rearranging happens on scales too small and too fast to witness directly. To glimpse that world, chemists have built tools that let light, magnetism, and motion speak for the unseen. These tools do not show pictures in the usual sense. Instead, they translate invisible behavior into patterns, peaks, and spectra, a language of lines that tells us what atoms are doing when no one is watching. Spectroscopy is the art of turning invisible energy into information. Each molecule, like a musical instrument, has its own resonant notes, frequencies at which it vibrates, absorbs, or emits light. When you shine radiation across a sample and measure what comes back, you get a fingerprint of those vibrations and transitions. That fingerprint can tell you not only what elements are present, but also how they are bonded, what shapes they form, and even how they move. It is the chemistry of listening, not looking. Infrared spectroscopy is one of the most elegant examples. Every chemical bond acts like a tiny spring connecting two atoms. When infrared light passes through a substance, some wavelengths are absorbed to make those springs stretch or bend. Each bond type, carbon-hydrogen, carbon-oxygen, nitrogen-hydrogen, absorbs at slightly different frequencies. The resulting spectrum looks like a series of dips and valleys, each one marking a vibration within the molecule. By reading those valleys, chemists can reconstruct the molecular structure, the way an experienced musician can name a chord after hearing a few notes. Raman spectroscopy offers a complementary way to hear those vibrations. Instead of measuring which light gets absorbed, Raman looks at how light is scattered. When monochromatic light, often from a laser, hits a molecule, most photons bounce back unchanged, but a few lose or gain energy as they interact with molecular vibrations, emerging slightly shifted in wavelength. Those shifts, tiny, precise, and distinctive, reveal the same vibrational fingerprints as infrared spectroscopy, but from a different angle. Raman spectroscopy is especially gentle, ideal for studying delicate materials, paintings, or even living cells without harm. Moving higher in energy brings us to ultraviolet and visible spectroscopy, where photons promote electrons to excited states. When light passes through a coloured compound, certain wavelengths are absorbed while others are transmitted or reflected. The pattern of absorption tells us about electronic structure, the arrangement of electrons in atoms and molecules. Transition metals, organic dyes and pigments all owe their colours to these electronic transitions. A chemist can tell whether a solution contains copper or cobalt just by the subtle differences in how they absorb light. Ultraviolet visible spectroscopy also reveals concentration. The more light absorbed, the more molecules are present. It's the same principle behind tinted sunglasses, just in a laboratory. We measure it with lasers and detectors rather than fashion. Then there's fluorescence, a phenomenon where absorbed light is re-emitted at a longer wavelength. Some molecules, after being excited by ultraviolet light, relax by giving off visible photons. This glowing return of energy is not only beautiful but highly informative. Fluorescent spectroscopy can track trace compounds in biology, monitor pollutants, or even measure the motion of single molecules. When a cell glows green or red under a microscope, it's not magic. It's chemistry turning invisible interactions into visible light. Beyond light, other tools reveal the unseen through magnetism. Nuclear magnetic resonance spectroscopy, or NMR, uses powerful magnetic fields to probe the tiny magnetic moments of atomic nuclei. When placed in a magnetic field, certain nuclei, like hydrogen or carbon-13, align with or against it. A short pulse of radio waves nudges them, and as they relax back into alignment, they emit signals that depend on their chemical environment. The result is a map of how atoms are connected in a molecule, their neighbours, and even their spatial arrangement. NMR is the quiet detective of chemistry, slow, deliberate, and incredibly revealing. From small molecules to proteins thousands of atoms large, it can sketch structures that no microscope could ever see. Mass spectrometry takes a different approach, using motion rather than light or magnetism. It turns molecules into ions, accelerates them through an electric field, and separates them based on their mass to charge ratio. Heavy ions move more slowly, lighter ones more quickly, and detectors record their arrival times as peaks on a graph. Each peak corresponds to a specific fragment or molecular weight, allowing chemists to piece together the original structure. It's a kind of molecular archaeology, reading the broken pieces to infer the whole. Mass spectrometry can identify compounds present at parts per billion, so sensitive that it can detect a single contaminant molecule in a sea of others. All of these instruments share one quiet challenge: separating signal from noise. In a perfect world, every spectrum would be crisp and clear, every peak distinct. But the real world is full of whispers, random fluctuations, stray electrons, environmental vibrations, and detector imperfections. The signal-to-noise ratio becomes the measure of trust. A strong signal rises confidently above the background hum. A weak one hides in it. Chemists learn to coax signals upward, using better detectors, longer acquisition times, and careful calibration. Sometimes, the most meaningful data lives just at the edge of audibility, where patience reveals what haste would miss. Calibration itself is its own form of ritual. Instruments are checked with standards, samples whose properties are known exactly, to ensure accuracy. A blank run containing only the solvent or background is recorded first to measure what nothing looks like. Subtracting that blank from the real sample's spectrum isolates the true signal. It's a kind of chemical mindfulness, a way of acknowledging the noise before searching for meaning within it. Error and uncertainty are not flaws in this process. They're companions. Every measurement carries a small margin of doubt, and good scientists learn to quantify that doubt rather than hide from it. Repetition builds confidence. When a peak appears at the same place across multiple trials, It stops being noise and becomes truth. Precision in chemistry isn't about eliminating uncertainty, it's about understanding it well enough to trust what remains. One of the quiet triumphs of modern spectroscopy is its ability to find things that were never meant to be found. Imagine testing drinking water and detecting a contaminant at a concentration of just a few parts per billion. That's like finding a single drop of dye in an Olympic-sized swimming pool. Yet instruments can do it, translating those faint molecular murmurs into unmistakable peaks on a screen. Such sensitivity protects health, ensures purity, and keeps us aware of the invisible threads that connect human life to the chemistry of its surroundings. There is a meditative rhythm to this kind of science. It demands stillness, patience, and humility. Instruments hum softly, samples rest in glass cuvettes, data appears line by line like quiet handwriting. The chemist waits, interprets, and listens. The reward is knowledge made from whispers, a translation of vibration, charge, and light into understanding. To see the unseen is to accept that light and matter speak in a language of probability, noise, and nuance. Each spectrum, each peak, is a message from molecules we cannot touch or see, a reminder that invisibility is not the same as absence. With the right tools, even the faintest signals reveal entire worlds that hum with quiet precision, waiting for someone patient enough to listen. Smell is the most ancient of the senses, and perhaps the most intimate. Long before sight or hearing evolved, early life already sensed the chemistry of its surroundings, the faint traces of food, danger, or company drifting through the water. Even now, every breath you take carries an invisible library of molecules that your brain turns into experiences, emotions, and memories. A single inhalation can transport you through decades. Chemistry becomes story, and the nose is its storyteller. The science of scent begins with volatility. To be smelled, a molecule must first be free to travel through the air. That means it has to be small enough and light enough to escape from whatever surface it came from. Volatile molecules are typically made of just a few dozen atoms at most, with structures that make them neither too water-loving nor too water-fearing. If they dissolve too easily in moisture, they'll never leave their source. If they're too heavy, gravity keeps them grounded. The perfect perfume molecule therefore lives in a delicate balance between stickiness and flight, ready to leap into the air, yet complex enough to linger when it lands in the nose. Once airborne, the molecules follow the path of the breath. They swirl through the nasal passages until they reach a patch of specialized tissue high inside the nose, the olfactory epithelium. There, about 400 different types of receptor proteins wait, each one folded into a unique shape. When a scent molecule bumps into a receptor that matches it, like a key sliding into a lock, a tiny electrical signal fires. That signal travels along a nerve to the brain, where it joins others to form a pattern. That pattern is the smell. But here's where the story becomes wonderfully complicated. Unlike vision or hearing, where one type of receptor handles a specific wavelength or frequency, smell works on a system of combinations. Each receptor can respond to many different molecules, and each molecule can activate several receptors at once. The result is a combinatorial code, a kind of chemical chord struck across the olfactory system. With just 400 receptors, the brain can recognize tens of thousands of different scents, each defined by its own unique combination of signals. The smell of rain, for example, may light up one particular arrangement of receptors, while cut grass triggers a slightly different one. Your perception of scent is essentially pattern recognition performed in chemistry, and it doesn't stop at recognition. The brain's olfactory centers are wired directly into the limbic system, which governs emotion and memory. That's why smells are so evocative, so unreasonably powerful. A few stray molecules can summon childhood summers, forgotten kitchens, or a person you haven't seen in years. The scent bypasses logic entirely, slipping past conscious thought to tap directly into feeling. You don't choose to remember, it just happens. Chemistry has found a shortcut to the heart. Consider the smell of rain, known as petrichor. It's one of the most universally beloved scents, yet it arises from an unlikely source. During dry spells, certain soil bacteria produce an organic compound called geosmin, which accumulates in the ground. When rain finally falls, the impact of droplets releases microscopic bubbles that burst into the air, carrying the geosmin with them. The human nose is astonishingly sensitive to it. We can detect geosmin at concentrations as low as a few parts per trillion. That means a single drop in an Olympic-sized swimming pool could be enough for you to notice. When we inhale that earthy freshness after rain, we're really reading a message from the soil, life announcing that the world has been watered again. The scent of cut grass tells another quiet story. When plants are wounded by mowing or grazing, they release a blend of molecules called green leaf volatiles, short-chain alcohols, aldehydes, and esters. These compounds aren't just accidental. They act as distress signals, warning nearby plants and attracting insects that prey on the herbivores responsible. To human noses, the same molecules create the unmistakable smell of summer, fresh and alive. It's the chemistry of plant defense, reinterpreted by the human brain as comfort and nostalgia. Then there's the smell of baking bread, which seems designed to make people happy. As dough bakes, heat triggers the Maillard reaction, a complex network of chemical changes between amino acids and sugars. The result is a cascade of volatile molecules, pyrazines, aldehydes, and furans, that drift through the kitchen in warm waves. Together they form the scent we associate with home, nourishment, and contentment. What feels emotional is really the work of hundreds of microscopic reactions, all whispering to the same part of the brain that stores memories of safety and satisfaction. Citrus oils tell a livelier tale. Peel an orange and you release bursts of tiny droplets from the skin, little pressurized sacs of limonene, pinene, and other terpenes. These molecules evaporate instantly, flooding the air with brightness. Limonene alone, though chemically simple, has a powerful psychological effect. Its structure interacts with receptors that the brain interprets as fresh or clean, which explains why so many cleaning products mimic citrus notes. What's funny is that the brain doesn't care whether it's natural or artificial. As long as the molecular key fits the receptor, the sensation is the same. Scent is democracy in chemistry. Every molecule gets an equal chance to tell its story. All these fragrances are made possible by the chemistry of volatility and the biology of pattern detection, but the meaning we attach to them is entirely human. A smell isn't just a set of molecules, it's an experience built from chemistry, memory, and context. One person's favourite perfume can be another's headache. The same smoke that smells like comfort at a campfire can trigger alarm in a kitchen. The molecules are identical. The stories they tell depend on the listener. In the perfume industry, understanding this chemistry is a kind of art. Perfumers, sometimes called noses, learn to blend hundreds of volatile compounds into complex harmonies. Some components evaporate quickly. These are the top notes that greet you first. Others linger longer, anchoring the fragrance in memory. The molecules themselves follow predictable laws of physics and chemistry, but their arrangement evokes pure emotion. It's a reminder that science and art often share the same raw materials. Smell also connects us to other species in remarkable ways. Dogs, for example, have around 300 million olfactory receptors, hundreds of times more than humans. they can detect a single molecule of certain substances among trillions of air molecules, tracking scents across vast distances. Moths can sense a single pheromone molecule released miles away by a potential mate. Compared to them, our own sense of smell is modest, yet it retains a power that none of the others possess: emotional depth. Your nose is, in a way, a molecular gossip columnist. It knows everyone's secrets. It can tell what someone had for lunch, whether a flower is blooming nearby, or whether rain is coming before a single drop falls. It reads the chemistry of the world constantly, storing impressions and linking them to moments in time. Each scent you encounter becomes part of a personal archive, ready to be recalled years later by the faintest trace of the same molecules. So much of life's beauty passes through the air unseen. The fragrance of a rose, the smell of soil, the crispness of winter air. Each is a conversation between chemistry and memory. With every breath, molecules whisper stories to the brain, and the brain responds with feeling. It's one of the quietest forms of communication there is, but perhaps also one of the most profound. In the invisible chemistry of scent, we find proof that memory, emotion, and matter are never as separate as they seem. The air around you is never truly empty. Even on the clearest day, it holds countless tiny travellers, droplets, dust, crystals, and chemical clusters so small that billions could fit inside a single raindrop. These suspended specks form the middle ground between gases and liquids, a world known as aerosols. They shape clouds, colours, and even climate, though they drift by unnoticed. Aerosols are chemistry in suspension, a dance of matter so fine it hovers between existence and invisibility. An aerosol is simply a collection of solid or liquid particles dispersed in a gas. Haze, fog, mist, sea spray, perfume, and even smoke are all examples. The word itself comes from aero, meaning air, and sol, meaning solution, a solution in the sky. Each particle can be as large as a grain of dust or as small as a virus, floating for minutes, hours, or even weeks before settling. They form through two main pathways: nucleation, where molecules gather spontaneously into tiny clusters, and condensation, where vapor condenses around existing particles. Nucleation is nature's way of building something from nothing. Imagine a humid atmosphere, full of water vapor molecules zipping through space. Most of them pass each other by, but occasionally a few stick together long enough to form a cluster. If the cluster is small, it quickly evaporates again. The pull of surface tension is too strong. But once the cluster reaches a critical size, it becomes stable, and more molecules begin to join. This marks the birth of a droplet. From there, condensation takes over, adding layer upon layer of vapor, building the droplet molecule by molecule. Surface tension plays a crucial role in this invisible architecture. It acts like a skin stretched tight around the droplet, resisting expansion. The smaller the droplet, the stronger the tension, meaning that very tiny droplets need higher humidity to stay intact. In this way, humidity and surface tension strike a delicate balance, constantly negotiating between growth and evaporation. The air may look still, but on the molecular level it's alive with competing processes. Some aerosols begin their lives with a helping hand from existing particles known as condensation nuclei. These can be anything from grains of salt lofted by ocean waves to soot from a candle flame or bits of pollen caught in the wind. Water vapor loves to cling to such surfaces, condensing more readily around them than in open air. The result is a microscopic shell of moisture that can grow into a visible droplet. Without these humble seeds, clouds would have difficulty forming. Pure air, even when saturated, often resists condensation, unless there's something for the water to hold on to. Salt, in particular, is an exceptional nucleus. When sea spray evaporates, it leaves behind tiny salt crystals that drift into the air. These hygroscopic particles, literally water-seeking, have an irresistible attraction to moisture. Even at relatively low humidity, they begin to absorb water, swelling as they go. This process, called hygroscopic growth, blurs the line between particle and droplet. What started as an invisible salt grain can expand into a shimmering mist droplet, reflecting sunlight and softening the horizon. It's why coastal air often feels heavier and looks hazier. The chemistry of the sea continues long after the waves break. This same principle shapes clouds high above. The sky is full of microscopic condensation nuclei, tiny pieces of dust, soot and salt that act as scaffolding for water vapor. As rising air cools, water molecules condense on these particles, forming countless droplets less than 1/100th of a millimeter wide. Alone, they are invisible. Together, billions of them scatter sunlight and create the white, cottony shapes that drift across the sky. The next time you look up at a cloud, you're seeing sunlight ricocheting off a suspension of droplets, each one a perfect balance of chemistry and physics. As droplets within a cloud collide and merge, some grow heavy enough to fall as rain. The journey from vapor to droplet to raindrop is a chain of tiny chances multiplied across vast numbers. Each stage depends on temperature, humidity, and the availability of nuclei. The result is both ordinary and extraordinary, every raindrop a chemical collaboration between air, water, and dust. Aerosols also influence how the sky looks and how sunlight reaches the ground. Small particles scatter short wavelengths of light, lending the sky its familiar blue. When the air fills with larger particles like smoke or volcanic ash, the scattering shifts toward red and orange, painting sunsets in vivid tones. Even the white glare of a hazy afternoon is the work of aerosols, diffusing sunlight into a soft glow that hides the sun's sharp edge. These optical effects, though purely physical, feel almost emotional, proof that chemistry can shape beauty without ever intending to. Closer to home, aerosols fill our daily lives in quieter ways. Every spray bottle and perfume atomizer creates a cloud of droplets small enough to float. The fizz of soda releases carbon dioxide bubbles that burst into miniature mists. Steam rising from a pot in the kitchen is another form of aerosol. Tiny droplets of water suspended in air, condensing into wisps as they cool. Even our breath, especially on a cold morning, reveals this process. The visible puff of condensation isn't smoke, it's a fleeting cloud formed from the moisture we exhale meeting the chill of the air. Nature, of course, is the great aerosol engineer. Sea spray, volcanic plumes, forest pollen and desert dust all lift particles skyward. Each source contributes to the planet's chemistry in its own way. Volcanic eruptions inject sulfur compounds that can reflect sunlight and cool the earth for years. Forest fires fill the air with organic aerosols that influence cloud formation. The oceans send out fine salt particles that seed clouds and even act as chemical reactors, scrubbing gases from the atmosphere. Through these invisible exchanges, aerosols help regulate the planet's temperature, climate, and rainfall. But while aerosols are often delicate and transient, their effects can be profound. A small change in particle composition or size can alter how clouds form or how sunlight scatters. Some aerosols warm the atmosphere by absorbing heat, while others cool it by reflecting light back into space. It's a reminder that even the softest mist can carry global significance, that chemistry at the tiniest scale can reach all the way to the climate itself. There's a certain poetry in how aerosols blur boundaries. They exist between states, neither fully gas nor fully liquid, neither fixed nor fleeting. Fog is perhaps the most graceful example, a ground-hugging cloud that turns air into something visible. Walk through fog and you move through 1,000,000 droplets brushing your skin, too small to feel but large enough to scatter light into a luminous haze. It's floating chemistry painting the sky. a natural watercolor that turns landscapes into soft silhouettes. Even the simplest fog holds astonishing complexity. Each droplet carries dissolved gases, trace ions and organic molecules gathered from the air. These tiny solutions undergo their own microchemistry, forming acids, reacting with pollutants, and exchanging ions with the particles around them. The fog is not static, it breathes. By the time it lifts, its chemistry has changed, and so has the air it touched. Aerosols remind us that the world is built on gradients, not absolutes. There's no clear line between solid and gas, between sky and sea, or between weather and chemistry. Everything mingles, drifts, and transforms. From perfume mist to mountain fog to towering clouds, these transient formations connect the intimate with the immense. The next time you see your breath in the cold, or watch morning fog roll over a field, think of the unseen balance that holds it all together. Surface tension, humidity, particle attraction, and the quiet pull of light. Every droplet hanging in the air tells a story of temperature, chemistry, and chance. For a brief moment, invisible molecules unite to make the air visible, and then, as always, they drift apart again, leaving only calm behind. The air around Earth is astonishingly thin. If you could shrink the planet down to the size of a classroom globe, the atmosphere would be no thicker than a coat of varnish on its surface. And yet, this delicate film of gases performs one of the most important balancing acts in nature. It keeps the planet comfortably warm. Without it, the average surface temperature would plunge well below freezing, the oceans would lock in ice, and life as we know it could not survive. The secret to this warmth lies in chemistry invisible to the eye, a quiet conversation between molecules and light known as the greenhouse effect. At first glance, the atmosphere seems transparent. Sunlight streams through it with ease, bathing the Earth in visible and ultraviolet light. The ground, the oceans, and the plants absorb that energy and later release it again, not as visible light, but as infrared radiation, a longer wavelength form of energy that carries heat. If all that infrared light escaped back into space unhindered, the planet would lose warmth almost as quickly as it gained it. But a handful of gases in the air absorb and re-emit that infrared radiation, trapping some of the heat and returning it gently to the surface. The result is not a sealed greenhouse, but a breathable, flexible blanket that keeps temperatures in the range where water can remain liquid and life can flourish. These so-called greenhouse gases make up only a small fraction of the air. The major components, nitrogen, oxygen, and argon, do not interact strongly with infrared light. Their molecular vibrations are symmetrical, meaning they lack the fluctuating electric fields that light can couple with. Infrared waves simply pass through them, like wind through an open window. But molecules such as carbon dioxide, water vapor, methane, and nitrous oxide have more complex shapes. Their atoms move asymmetrically when they vibrate, creating tiny oscillating electric fields that can absorb specific frequencies of infrared radiation. Each molecule resonates with its own set of vibrational modes, soaking up energy at particular wavelengths like a finely tuned instrument. Water vapor is the most abundant of these gases and the most flexible. It can bend, stretch, and twist in many ways, absorbing heat across a broad range of infrared frequencies. Carbon dioxide, though far less abundant, is a powerful contributor because it absorbs strongly in the wavelengths where water vapor absorbs less, what scientists call the atmospheric windows. These are parts of the infrared spectrum where energy can escape freely to space unless another gas happens to be there to catch it. Methane and nitrous oxide add their own subtle layers to this invisible filter, each intercepting different bands of radiation. Together they shape how energy moves through the atmosphere, like a set of invisible curtains filtering light from the surface to the stars. The beauty of this system lies in its balance. During the day, the Earth absorbs sunlight. At night, it radiates infrared energy back outward. Greenhouse gases slow this cooling process, ensuring that not all the heat escapes at once. It's a self-regulating rhythm that has kept the planet's temperature within life-friendly limits for millions of years. This natural warming effect, about 33 degrees Celsius warmer than a bare rock in space, makes Earth unique among its neighbours. The Moon, which lacks an atmosphere, experiences temperature swings of hundreds of degrees between day and night. Venus, cloaked in an atmosphere thick with carbon dioxide, traps almost all of its heat, turning its surface into a furnace hot enough to melt lead. Earth sits delicately between those extremes, wrapped in a blanket that is mostly comfortable, though sometimes a little too cozy. When scientists talk about radiative forcing, they mean the balance between energy coming in and energy going out. Positive forcing means more energy is retained, negative forcing means more is lost. Greenhouse gases increase positive forcing by absorbing outgoing infrared light and re-emitting some of it downward. The effect is cumulative, not instantaneous. Like adding an extra layer to a blanket, the warmth doesn't come all at once. It builds slowly, over years and decades, as the energy equilibrium adjusts. Water vapor introduces a fascinating feedback loop. Warmer air can hold more moisture, and more moisture amplifies the greenhouse effect because water vapor itself traps heat. It's not the initial spark, but the echo that follows it. Clouds, made from condensed water droplets, complicate the story further. They both warm and cool the planet, depending on their type and altitude. Thin, high clouds tend to trap heat like greenhouse gases, while thick, low clouds reflect sunlight back into space, producing a cooling effect. The planet's temperature depends on the balance of these opposing influences, a dynamic interplay of light, vapor, and geometry. Another quiet feedback involves ice and snow. Bright surfaces reflect most of the sunlight that hits them, helping keep the planet cool. When ice melts, darker land or water beneath absorbs more sunlight, increasing local warming. That extra warmth melts more ice, setting up a loop that accelerates itself. Even here, the chemistry of the air plays a role. Greenhouse gases warm the surface, altering the balance between ice, water, and vapor, and the process feeds back into the atmospheric chemistry that started it. What makes greenhouse gases so effective is not their abundance but their persistence. Water vapor cycles out of the atmosphere quickly, in days or weeks, as rain or snow. Carbon dioxide, methane, and nitrous oxide linger for years, decades, or even centuries. Each molecule may be invisible, but in the aggregate they create a memory of energy, a record of sunlight stored in motion. Over long timescales, these gases interact with oceans and rocks, dissolving, reacting, and rebalancing through slow geological chemistry. The carbon dioxide we exhale today may one day be locked in limestone, or dissolve into seawater, or return to the air through volcanoes. The planet's thermostat works on every scale, from the flicker of a raindrop to the age of mountains. Despite its name, the greenhouse effect is not a trap but a flow, a balance between incoming solar energy and outgoing infrared radiation. Without greenhouse gases, Earth's nights would be bitterly cold, its oceans frozen, and its ecosystems impossible. With too much, warmth accumulates faster than it can escape, shifting climates and weather patterns. Yet the underlying chemistry remains the same. Photons absorbed, bonds stretched and released, energy redistributed across the thin veil of air that separates Earth from the vacuum of space. The physics of infrared absorption can be surprisingly elegant. Each vibrational mode of a molecule behaves like a spring, oscillating at a frequency determined by the mass of its atoms and the stiffness of its bonds. When infrared light of the right wavelength passes by, the oscillation strengthens, capturing the photon's energy. Later, the molecule releases that energy again, radiating it in random directions. Some of those photons head upward into space, while others head downward toward the surface. The atmosphere glows faintly in infrared light all the time, a quiet exchange between earth and sky, invisible to our eyes, but measurable with instruments that see heat instead of colour. Think of the atmosphere as a conversation of photons. Sunlight speaks in short wavelengths, the ground replies in longer ones, and greenhouse gases act as interpreters, repeating part of the message back downward. The planet stays warm not because energy is trapped, but because it is shared, recycled, and delayed. The system breathes, absorbing, emitting, and rebalancing in ceaseless rhythm. There's a quiet reassurance in that image. The chemistry that warms the Earth is the same chemistry that allows clouds to form, plants to grow, and oceans to stay liquid. It is not a villain or a miracle, simply a mechanism, one that has kept this planet's climate habitable through countless cycles of change. The atmosphere wears a thin, invisible blanket, mostly comfortable, sometimes a little too cozy, but without it, the world would be far too cold for the warmth of the life. High above the Earth, sunlight and oxygen perform a quiet act of alchemy. Invisible rays of ultraviolet light strike molecules of oxygen, splitting them apart into single atoms that drift momentarily through the air before finding new partners. When one of those free atoms collides with an intact oxygen molecule, the result is ozone, a trio of atoms bound together in a fragile, energetic embrace. Ozone is chemistry's reminder that even something as familiar as oxygen can change character completely with just one extra bond. The same element that keeps us alive at the surface becomes, a few dozen kilometers higher, the planet's sunscreen. Ozone's story is one of balance. In the stratosphere, where sunlight is strong, ozone continually forms and breaks apart. Ultraviolet light both creates it and destroys it. Each molecule lasts only minutes before being split again, but as long as the cycle continues, the overall concentration remains steady. That shimmering layer of ozone absorbs much of the ultraviolet radiation that would otherwise scorch the surface, shielding life from harm while itself living on borrowed time. Lower in the atmosphere, ozone tells a very different tale. Near the ground, it's no longer a guardian but a sign of overactivity, born not from natural balance but from pollution and sunlight colliding in the wrong place. Yet even here, ozone is only one player in a much larger drama, the chemistry of radicals, the restless intermediates that drive the sky's constant cleanup. A radical is a molecule or atom with an unpaired electron, a tiny imbalance that makes it extraordinarily reactive. These molecules are fleeting, existing for milliseconds or seconds at most, but during their short lives they shape the entire chemistry of the air. The hydroxyl radical, often written as OH, is the most important of them all. Chemists sometimes call it the detergent of the atmosphere, because it reacts with almost every pollutant it encounters, stripping electrons, rearranging bonds and turning stubborn gases into more manageable forms. The formation of hydroxyl radicals begins when ultraviolet light interacts with ozone or water vapor, freeing fragments that immediately seek partners. Once born, the OH radical starts a cascade of reactions, oxidizing carbon monoxide into carbon dioxide, breaking down methane, and cleaning volatile organic compounds into simpler molecules that can dissolve in rain or settle to the ground. It's a microscopic spring cleaning happening continuously, invisible but essential. Without radicals, the air would slowly fill with unreacted gases, smog would linger indefinitely, and the delicate chemistry of the atmosphere would grind to a halt. Nitrogen oxides, molecules of nitrogen and oxygen collectively called NOx, join this invisible dance. They shuttle between forms, nitric oxide, nitrogen dioxide, and other reactive variants. During daylight, sunlight splits nitrogen dioxide into nitric oxide and a free oxygen atom, which can combine with oxygen gas to produce ozone. At night, the reactions shift again, building reservoirs of nitrates that dissolve with morning dew. This balance between creation and destruction, driven by light, temperature, and chance encounters, defines the rhythm of the lower atmosphere. Then there are the organic radicals, peroxy and alkoxy species, often abbreviated as RO2 and RO. They form when hydrocarbons, released by plants or engines, meet the hydroxyl radical. These carbon-based radicals are the middlemen of smog chemistry, passing oxygen atoms around like dancers trading partners in a crowded hall. Some reactions clean the air, converting pollutants into harmless products. Others build more ozone or form fine particulate matter. The result depends on subtle details: how much sunlight, how much nitrogen oxide, how many reactive molecules are present. The chemistry of the air is not a simple sequence, but a network of intersecting pathways, adjusting itself with every sunrise. Despite their chaotic nature, radicals serve as nature's custodians. They are, as one might say, the party guests who clean up while dancing. They rush through the atmosphere, colliding, transforming and vanishing, tidying the excesses left by both natural processes and human activity. Their energy makes them short-lived, but indispensable. No one ever sees them directly, yet their fingerprints are everywhere, in the scent of rain after lightning, in the gradual fading of pollutants after a sunny day, in the faint haze above a busy city that clears when the weather changes. Lightning is one of the atmosphere's radical artists. The tremendous heat of a lightning bolt, hotter than the surface of the sun, splits nitrogen and oxygen molecules apart, creating a burst of reactive nitrogen oxides that later form nitrates, returning to Earth in rainfall as natural fertilizer. It's a brief but powerful chemical storm, converting atmospheric stability into reactivity and back again within seconds. The life of a radical is astonishingly brief. A hydroxyl radical, for example, may exist for less than a second before reacting with something nearby. But multiply that by billions upon billions, and the cumulative effect becomes enormous. Every second, trillions of these unseen molecules are shaping the composition of the atmosphere. They transform gases, neutralize toxins, and help maintain the balance that keeps air breathable and skies clear. They are chemistry's most tireless workers, performing their duties at speeds too fast for any eye or instrument to see directly. Smog is where this invisible chemistry becomes visible. In urban air, sunlight acts as the conductor, orchestrating reactions between nitrogen oxides, volatile organic compounds, and oxygen. Early in the morning, traffic releases fresh pollutants. As the day warms, hydroxyl radicals and sunlight begin rearranging them, producing ozone and other photochemical byproducts. By afternoon, the air takes on a bluish haze, a delicate fog of molecules suspended in equilibrium between creation and breakdown. By nightfall, the chemistry slows as the light fades, leaving the city to cool and the radicals to rest until sunrise stirs them again. It's easy to think of smog as purely negative, but chemically speaking, it's a complex conversation. Every molecule of ozone or peroxide formed in smog is part of a chain that will eventually end in stability. Carbon dioxide, water, nitrates, and dust that returns to Earth. The system, for all its turbulence, trends toward balance. What we see as pollution is often chemistry still in progress. In the upper atmosphere, ozone chemistry continues its own balancing act. High-energy ultraviolet light splits oxygen molecules apart, forming ozone, while slightly lower-energy photons break ozone back down again. The two processes occur at nearly the same rate, maintaining a steady shield around the planet. The system is so finely tuned that a small change in the concentration of radicals, chlorine or bromine atoms from human-made compounds for instance, can tip the balance, speeding up ozone destruction. Fortunately, those reactive intruders are disappearing from the atmosphere, and the protective layer continues its slow recovery, molecule by molecule. What ties all these processes together is motion, molecules colliding, splitting, and recombining in endless repetition. The atmosphere is never static. It's a living chemical network. Radicals flicker in and out of existence. Ozone appears and disappears, and yet the overall system remains steady. It's a balance maintained not through stillness but through perpetual change. The chemistry of the sky reminds us that stability doesn't mean silence. Above every landscape, the air hums with activity so constant and rapid that stillness is only an illusion. Ozone forms and fades, radicals dance and vanish. Sunlight writes and erases chemical equations faster than thought. Yet through all this ceaseless motion, the air stays breathable, the light stays gentle, and life goes on below, unaware, but always protected by the reactive grace of the atmosphere. Transparency seems like the absence of something, the lack of colour, the absence of obstruction, but in truth, it's an achievement. For light to pass through matter untouched, the atoms inside must cooperate in an extraordinary way. They must hold their electrons just tightly enough that photons slip by without being absorbed, yet not so rigidly that the light is scattered. The result is one of nature's quiet miracles. Glass that looks like nothing, water that hides its presence, crystals that seem to vanish when submerged in oil. Seeing through something isn't simple at all. It's physics, chemistry, and geometry in perfect harmony. When light encounters matter, one of three things can happen. It can be absorbed, scattered, or transmitted. Absorption occurs when the light's energy matches the energy needed to move an electron to a higher state. Scattering happens when light bounces off irregularities, atoms, particles, or surfaces, sending it off in many directions. Transmission is the rare case where neither of these dominates, allowing the light to pass through with little interruption. Transparency, therefore, is not emptiness but balance. It's the state where matter says to light, "You may pass, but please behave yourself." The key to that balance lies in the structure of electrons within a material. In atoms and molecules, electrons occupy specific energy levels. In solids, where atoms are packed together, these levels form bands, broad ranges of energies that electrons can occupy. Between these bands lie forbidden regions called band gaps. If the energy of a photon is smaller than the band gap, it cannot excite an electron from one band to another. The photon passes through unabsorbed, like a runner who finds the gate locked and simply keeps running. If the photon's energy is higher than the gap, the electron can jump and the light is absorbed. This is why glass, quartz, and pure water are transparent in the visible spectrum but not in the ultraviolet. Their band gaps are wide enough that visible light lacks the energy to be absorbed, but ultraviolet light is energetic enough to excite electrons so it doesn't make it through. The same principle explains why metals are opaque. Their electrons can move freely in partially filled bands, meaning almost any photon can be absorbed or reflected. Transparency, in other words, is what happens when the photons of visible light find no resonance in the electronic structure of matter. But even when absorption is minimal, scattering can still spoil the view. The colour of the sky, the haze of milk, and the shimmer of frosted glass all arise from light scattering off tiny irregularities. When particles are much smaller than the wavelength of light, like molecules in the atmosphere, they produce Rayleigh scattering, which is stronger for short wavelengths. That's why the sky appears blue. Shorter, bluer wavelengths scatter more efficiently than longer, redder ones. When the particles are closer in size to the wavelength, scattering becomes wavelength independent, known as me-scattering. That's the reason clouds are white. Droplets in the cloud scatter all colours equally, blending them into brightness. For a material to appear truly transparent, its internal structure must be almost perfectly uniform, with no particles or defects comparable in size to visible light's wavelength. That's an incredibly small requirement, roughly a few hundred nanometers. Glass achieves this by cooling a molten liquid so quickly that its atoms never arrange into a repeating crystal lattice. The result is an amorphous solid, smooth and uniform at the scale of light. Photons pass through, barely noticing they've encountered a solid at all. Crystals can also be transparent, though for a different reason. In quartz or diamond, the atomic lattice is so precisely ordered that light waves travel through it coherently, scattering only slightly at each atom before continuing forward. The effect is like a crowd parting in perfect rhythm. Each atom steps aside at exactly the right time, letting the light weave through unbroken. This is light slipping quietly through lattices, one photon after another. Refraction, the bending of light as it passes between materials, is another piece of this story. When light slows down upon entering a denser medium, its direction changes. The amount of bending depends on the material's refractive index, a measure of how much it delays the light. Glass bends light enough to make lenses possible. Water bends it just enough to make a straw look crooked in a glass. Diamonds, with their high refractive index, scatter light internally so strongly that we see brilliance and fire instead of simple clarity. Transparency doesn't mean invisibility, it means control. The best transparent materials shape light without losing it. Reflection, meanwhile, is the flip side of transmission. At every boundary between materials of different refractive indices, some portion of light bounces back. That's why even the clearest glass reflects a faint image of the world behind you. Reflection increases when the difference between media is greater. It's also why a wet road glistens in sunlight. The water creates a new interface with air, changing how light refracts and reflects, turning dull asphalt into a temporary mirror. Water is a masterclass in partial transparency. A shallow pool looks clear because visible light passes through it easily, but in deeper water, red wavelengths are absorbed first, followed by orange and yellow. Only blue penetrates to great depths, giving the ocean its characteristic hue. The water molecules vibrate in response to infrared light, absorbing heat, while ultraviolet is swallowed by electronic excitations. The visible range sits safely in between, an accidental window of transparency that allows sunlight to reach beneath the waves and power photosynthesis in the sea. Plastics, another family of transparent materials, manage their clarity through chemistry. Polymers like acrylic and polycarbonate consist of long, tangled chains of carbon and hydrogen. Their molecular bonds have energy gaps wide enough to ignore visible light. However, any additives, impurities, or tiny crystalline regions can scatter light and make the plastic cloudy. This is why some plastics yellow or haze over time. Small structural changes introduce scattering centers, and photons begin to lose their way. Transparency, it turns out, is delicate. It requires molecular discipline. Nature offers its own transparent marvels. Ice, when pure and free of bubbles, can be as clear as glass, though snow, made of countless tiny crystals, appears white because each crystal boundary scatters light. The same material, arranged differently, transforms from invisible to opaque. Human-made materials follow the same rule. Polish a surface smooth and remove imperfections, and clarity emerges. Roughen it slightly, and light fragments into reflections and blur. The boundary between clear and cloudy is often only a few nanometers wide. Transparency is also an illusion of perspective. We tend to think of clear materials as empty, yet they're as dense and complex as anything else. Every cubic centimetre of glass contains roughly 10 quadrillion atoms, each interacting with the light according to the laws of quantum mechanics. That we can see through such density at all is astonishing. It's as if the atoms collectively agree to step aside, to let the photons slip through in peace. When light moves through a transparent material, it doesn't actually travel in a straight line. It dances. The electromagnetic field interacts with electrons, inducing tiny oscillations that briefly delay the wave before re-emitting it. This repeated pause-and-go motion gives the illusion of slower speed. The light is constantly being borrowed and returned, absorbed and re-emitted so quickly that no one photon ever stays long enough to be trapped. Transparency, then, is cooperation on a microscopic scale, matter and light taking turns with grace. So the next time you look through a window, remember that what seems simple is a masterpiece of molecular order and restraint. The glass doesn't ignore the light, it negotiates with it. It refracts, reflects, and delays it just enough to keep it whole. Diamonds dazzle by scattering, water soothes by letting light glide through. In all cases, transparency is not the absence of interaction, but the perfection of it. A quiet agreement between photons and matter that allows the world beyond to be seen. For most of history, transparency was a natural gift, something found in quartz, water and glass, not something humans made on purpose. But in recent decades, science has begun to play with light in increasingly clever ways, designing materials that guide, bend, or even hide it. Where nature achieves transparency through simplicity, humans now chase invisibility through precision. From nanoparticles smaller than bacteria to metamaterials structured finer than the wavelength of light, the modern age of optics is about sculpting the unseen. You could say engineers are trying to outdo glass at its own job. At the heart of this pursuit lies nanophotonics, the study of how light interacts with matter on the scale of nanometers, billionths of a meter. At this size, materials stop behaving like their bulk selves and start developing strange tunable properties. Gold, for instance, seems immutable in its yellow luster, but shrink it down to particles just a few dozen atoms wide and it turns ruby red. This happens because of a phenomenon called plasmonic resonance. In a metal, electrons can move freely, and when light hits a tiny particle, those electrons collectively oscillate at a specific frequency. Depending on the size of the particle and the wavelength of light, some colours are absorbed and others are reflected, producing vivid hues. Medieval stained glass artisans unknowingly harnessed this principle centuries ago, mixing nanoparticles of gold or silver into glass to create the deep reds and yellows still glowing in cathedrals today. Now, scientists do the same with deliberate control. By adjusting particle size, shape and composition, they can fine-tune how nanoparticles interact with light, creating materials that reflect, absorb, or transmit specific colours. The same principle powers modern applications from medical imaging to solar panels. Plasmonic nanoparticles can convert light into heat with remarkable efficiency, allowing targeted cancer therapies that warm and destroy cells with pinpoint accuracy. On the other end of the spectrum, they can concentrate light into nanoscale volumes, improving the sensitivity of sensors that detect single molecules. It's chemistry turned into choreography, electrons dancing in rhythm with light. Quantum dots take this control a step further. These are tiny semiconductor crystals so small that their electronic properties are determined by quantum mechanics rather than bulk chemistry. When excited by light, they re-emit photons at precise wavelengths depending on their size. Make a quantum dot smaller and its emission shifts toward blue. Make it larger and the glow drifts toward red. This tunability has made them the darlings of display technology. Televisions and monitors that boast quantum color owe their brilliance to layers of these dots converting backlight into perfectly pure reds, greens, and blues. What once required pigments and filters now comes from quantum-sized control over how electrons absorb and release light. Thin films add yet another layer to the human pursuit of invisibility. When light reflects from multiple layers only a few hundred nanometers thick, some wavelengths interfere destructively and cancel out while others reinforce each other. This is why soap bubbles shimmer with iridescence. The film is so thin that light waves overlap and interfere. Engineers have learned to reproduce and manipulate that effect deliberately. Anti-reflective coatings on glasses, camera lenses and solar panels use carefully stacked layers to cancel reflections while enhancing transmission. Some materials can be made so non-reflective that they appear like holes cut in reality, black surfaces that seem to swallow light entirely. These coatings rely on nanostructures that trap photons through multiple reflections, giving them no chance to escape. The result looks less like a surface and more like an absence, but the most ambitious attempt to control light comes from metamaterials, artificial structures designed to guide electromagnetic waves in ways natural materials never could. Rather than relying on chemical composition, metamaterials derive their properties from geometry. Arrays of microscopic loops, pillars, and resonators act as tiny antennas, interacting with light at scales smaller than its wavelength. By adjusting these patterns, scientists can craft materials with negative refractive indices, substances that bend light in the opposite direction to normal. In a conventional material like water or glass, light slows down and bends toward the denser medium. In a metamaterial with a negative index, the opposite happens. Light refracts backward, curving around objects rather than striking them head-on. The concept first demonstrated in the early 2000s was met with awe and disbelief. A sheet of metamaterial could, in theory, make objects appear to vanish by guiding light smoothly around them, returning it to its original trajectory as if nothing were there. It wasn't magic. It was mathematics woven into matter. Practical cloaking remains challenging, of course. Early devices worked only for microwaves, not visible light, and only within narrow wavelength ranges. Scaling the structures small enough to handle the much shorter wavelengths of visible light is a formidable engineering task. Even when successful, such cloaks often work from specific angles or under controlled conditions. True invisibility, the kind that would let you vanish into thin air, remains more dream than device. But the fact that it is even possible, even momentarily, feels like a triumph. Humanity has learned to sculpt the path of light itself, if only in small shimmering glimpses. Outside the laboratory, these ideas have found practical uses. Metamaterials can create super lenses that capture details smaller than the wavelength of light, breaking what was once considered a fundamental limit of resolution. They can also shape radar and radio waves for stealth technology, guide heat flow for thermal management, and improve antennas for faster communications. In many cases, invisibility isn't the goal. Efficiency is. A solar panel that traps every photon, a screen that wastes no light, or a coating that hides imperfections, all are echoes of the same pursuit, the human desire to master the invisible. There's a philosophical symmetry to all this. Nature made transparency look effortless. Glass, water, and air, achieving it simply by not interacting too strongly with light. Humans, on the other hand, have achieved invisibility through complexity, by designing interactions so precise that light is bent, delayed, and redirected without noticing the trick. One approach depends on passivity, the other on orchestration. Transparency is nature's serenity. Invisibility is humanity's ingenuity. In the end, both reveal the same truth. Light is persuadable. It can be coaxed, guided, and shaped by matter, whether by the lattice of a crystal or the pattern of a nanostructure. And every time scientists succeed in bending it, they illuminate not just the world, but the art of perception itself. What we call invisibility is not the absence of light, but the mastery of its conversation with matter. Somewhere between a raindrop and a laboratory mirror, the story of light continues, waves slipping quietly through glass, scattering in mist, or curling invisibly around a man-made metamaterial. The boundaries of visibility are no longer dictated solely by nature. We now build our own windows, mirrors, and illusions, and perhaps that's the most poetic part of all. After centuries of studying the way light reveals the world, humans have learned how to make it look away. The world we live in is quietly engineered by the unseen. Every day, billions of invisible particles work in silence, making surfaces smoother, screens brighter, and sunlight a little less harsh on the skin. The age of the nanoworld isn't somewhere in the future, it's already here, woven into sunscreen, electronics, and even the coatings on your glasses. The smallest structures now deliver some of the biggest comforts. It's the story of tiny work, big comfort. Take sunscreen, for example. For centuries, protecting skin from the sun meant painting it white with thick pastes of zinc oxide or titanium dioxide. These minerals worked wonderfully. They reflected and scattered ultraviolet light, shielding skin from burns and long-term damage. But they also left faces looking like porcelain masks. The transformation came when scientists learned to make the same materials on the nanoscale. Shrunk down to particles only a few billionths of a meter across, titanium dioxide and zinc oxide still block ultraviolet light, but no longer scatter visible light. The cream becomes transparent, forming an invisible shield that reflects away harmful rays while letting ordinary sunlight pass through. You could say nanotechnology taught sunscreen how to disappear. These nanoparticles don't just protect, they perform delicate optical tricks. Their size is tuned so that they scatter ultraviolet wavelengths most effectively, while minimizing the scattering of visible light. It's like having a bouncer who blocks only the troublemakers at the door, letting everyone else in. The science behind it is simple yet elegant, small enough to be invisible, large enough to defend. They form a barrier that doesn't absorb light or heat up, reducing irritation for sensitive skin and increasing durability in water and sweat. Sunscreens today owe their easy, clear finish to chemistry that operates below the threshold of sight. The same invisible craftsmanship coats countless other surfaces around us. Car windshields, eyeglasses, camera lenses, and even bathroom mirrors now use nanoscopic films to repel water, resist fog, and shrug off dirt. These coatings are built using the concept of hydrophobicity, literally fear of water. On a smooth surface, water tends to spread, forming thin films that fog or streak. But on a surface textured at the nanoscale, droplets can't spread out. Instead, they sit like beads on a lotus leaf, rolling away with gravity or the faintest breeze. The result is a self-cleaning effect so efficient it seems magical. Raindrops take the dust away as they go, leaving glass clear and spotless. This idea of mimicking nature's nanostructures comes directly from biology. The lotus leaf's microscopic bumps and waxy coatings inspired a generation of scientists to recreate its water-shedding properties in synthetic materials. Now, these hydrophobic coatings are everywhere, from solar panels that clean themselves in the rain to building facades that resist grime. Even the anti-fog layer on swimming goggles works by controlling water behavior at the nanometer scale, spreading droplets so thinly that they can't scatter light. The line between chemistry and convenience has never been thinner. literally. In electronics, the nano world has become the foundation of modern life. Every microchip, every phone, and every television screen is built on structures so small that they operate at the edge of quantum mechanics. Circuits once measured in millimeters now count their features in nanometers. The transistors inside your computer switch on and off faster than the blink of an eye, controlling electrical currents through paths thinner than a virus. Shrinking these components doesn't just make devices smaller, it makes them smarter, faster, and more energy efficient. Quantum dots, those glowing nanocrystals that once seemed like pure laboratory curiosities, have now moved into living rooms. When struck by light, each quantum dot emits a color determined by its size. Smaller dots glow blue, larger ones glow red. This tunability has revolutionized display technology, producing screens with richer colors and higher efficiency. Instead of using dyes or filters, modern displays rely on quantum precision, translating nanoscale dimensions into visual brilliance. It's nanophotonics repurposed for comfort and entertainment, the physics of the very small illuminating the details of the everyday. Sensors too have shrunk into the nanoscale, becoming more sensitive than ever before. Nanostructured materials can detect single molecules of a gas or trace amounts of pollutants in water. A few atoms of gold or graphene layered over a sensor's surface can amplify signals or change color when exposed to specific chemicals. These technologies are used to monitor air quality, detect toxins, and even diagnose diseases from breath samples. Each device is a miniature chemical laboratory, working invisibly to keep environments safe and healthy. But as with all powerful tools, the nano world demands respect. The very small can behave unpredictably. Nanoparticles, because of their size and high surface area, interact more readily with biological tissues than their bulk counterparts. Scientists study how they aggregate, dissolve, or persist in the environment, ensuring they remain safe for use in cosmetics, medicine, and industry. Many nanoparticles, like those in sunscreens, are designed to be insoluble and inert, passing harmlessly through skin or rinsing away. Others are coated with stabilizing molecules that prevent unwanted reactions or clumping. Responsible nanotechnology isn't just about building, it's about understanding and restraint. In medicine, this careful approach becomes an art. Nanoparticles can deliver drugs directly to specific tissues, reducing side effects and improving efficiency. Some are built to recognize diseased cells, releasing their cargo only where needed. Others can slip through biological barriers that larger particles can't cross. It's targeted treatment at the molecular level, with each particle a courier designed for precision delivery. Yet for all their sophistication, these technologies are guided by a simple principle, using smallness to achieve gentleness. Even the clothes we wear can carry invisible helpers. Fabrics coated with nanoscale silver particles resist bacterial growth and odors. Sportswear made with nanofibers breathes more easily while repelling moisture. Paints and varnishes contain nanoceramic additives that make them scratch-resistant and longer-lasting. These improvements don't change how things look or feel, they simply make them perform better, for longer. The world's texture hasn't changed, but its chemistry has. The real marvel of the nano world is how seamlessly it hides in plain sight. You can't see the coatings on your glasses, the nanoparticles in your sunscreen, or the quantum dots in your TV, but their presence defines the comfort of modern life. They make colours sharper, air cleaner, electronics smarter, and daily routines smoother. Every invisible layer and particle works quietly, without drawing attention, serving the simple human desire for ease and safety. Still, there's something poetic about it. We live surrounded by invisible collaborations, atoms engineered to improve the light that reaches our eyes, or the water that rolls off our windows. What once required force or bulk now happens through finesse. Technology has learned to whisper. The nanoworld doesn't overwhelm the senses, it refines them. It's the elegance of smallness, the science of restraint. Whether it's a sunscreen that vanishes on the skin, a coating that keeps glass perpetually clear, or a display that glows with impossible colour, all of it comes from mastery over the invisible. The future may bring new uses and new questions, but the principle will remain the same. The smallest actions can create the largest comforts, and the quietest chemistry can make the loudest difference. If you could pause the world for a moment, suspend every scent, every flicker of heat, every breath, you'd discover that almost everything you experience is built from invisible chemistry. The sizzle of food, the rhythm of breathing, the smell of rain, even the calm that follows a cup of tea, all of it comes from unseen exchanges of molecules, electrons, and energy. The visible world, for all its colour and motion, is just the thinnest surface of a deeper, ceaseless conversation. In truth, invisibility is the rule, and visibility the rare exception. Nowhere is this quiet chemistry more familiar than in the kitchen. It's the most approachable laboratory on Earth, full of experiments that smell delicious and yield dinner instead of data. Take fermentation, for instance. Beneath the bubbles of bread dough or the tang of yogurt lies a microscopic civilization of yeast and bacteria, transforming sugars into acids, alcohols, and gases. Each bubble of carbon dioxide released by yeast in a loaf of bread is a whisper of invisible respiration, the same fundamental chemistry that happens inside our own lungs. When dough rises, it's really just exhaled breath trapped in flour and water, expanding quietly into a meal. The Maillard reaction, the chemistry behind browning, adds another layer of invisibility to the plate. When heat strikes proteins and sugars, they rearrange into hundreds of new compounds, creating the complex aromas and golden hues of roasted coffee, seared meat, and baked bread. None of it is visible at the start. It begins with electrons shifting, bonds twisting, and water leaving the scene. What your eyes see as colour change is just the end of a long invisible dance between carbon, hydrogen, oxygen, and nitrogen atoms. Cooking, at its core, is chemistry slowed down just enough for us to smell its progress. Even the aroma of a meal spreading through a room is diffusion in motion, volatile molecules leaving the pan and finding their way to your nose, carried by tiny currents of air. A single sniff is a summary of thousands of invisible travellers, each molecule bouncing, colliding, and scattering until it fits neatly into a receptor that translates its shape into memory. The warmth of baking bread or the spiciness of garlic feels emotional, but beneath it all is a patient flow of atoms migrating through air, connecting stove to brain. The same invisible chemistry hums inside the body, keeping every moment alive without fanfare. Every breath you take is an exchange of gases across microscopic membranes. Oxygen enters, carbon dioxide leaves, and hemoglobin ferries molecules with clockwork precision. The carbon dioxide you exhale becomes food for plants, which in turn release the oxygen you breathe again, a silent recycling loop powered by invisible light and invisible gases. You can't see it, but you participate in it with every heartbeat. Inside your cells, even quieter dramas unfold. Neurotransmitters jump between neurons in bursts of molecules too small to imagine, carrying thoughts, sensations, and moods. Dopamine, serotonin, and acetylcholine flicker in and out of existence, each acting for mere seconds before being reabsorbed or broken down. The thoughts that shape your day are built from molecular trades so small and fast they would vanish before light could reach them. Hormones, meanwhile, play the slower, subtler symphony. Chemical messengers drifting through blood, guiding everything from appetite to sleep to love. Adrenaline sharpens focus, melatonin dims awareness, oxytocin softens the edges of stress. The body is not a machine made of parts, it's a sea of interacting molecules, chemistry in perfect equilibrium. Even emotions, those ineffable sensations that seem beyond measurement, are governed by the chemistry of invisibility. A surge of joy is a cascade of molecular signals. A moment of calm, a gentle drop in cortisol, the feeling of connection, an invisible bloom of neurotransmitters weaving through synapses. Every heartbeat, every sigh is chemistry keeping rhythm. Step outdoors, and the unseen continues its work on a planetary scale. The air you walk through is alive with invisible activity. Soil bacteria quietly fix nitrogen, turning the unreactive gas that fills most of the atmosphere into compounds plants can use. Without them, the green of the world would fade. Every leaf depends on this microbial labour force buried just beneath our feet. The scent of freshly turned soil, the comforting, earthy smell after rain, comes from a molecule called geosmin, released by those same bacteria as they breathe and multiply. It's one of the few invisible processes that announces itself to the nose, reminding us that the ground is not inert but breathing. When rain begins to fall, droplets sweep through the air, gathering ions and aerosols. The collision of water and dust releases faint electric charges, ionizing molecules and intensifying the scent of the storm. Lightning, a giant discharge of electricity, creates radicals that briefly clean the atmosphere, oxidizing pollutants into simpler forms. Even as thunder rumbles, the chemistry of the air resets itself, one more invisible cycle renewed. The oceans perform their own unseen magic. When waves crash and break, they fling tiny droplets of seawater into the air. As these droplets evaporate, they leave behind salt crystals, microscopic seeds that help form clouds. The connection between ocean and sky is literal, written in sodium and chloride ions drifting upward to shape weather. Every cloud is born of this invisible partnership between sea and air, a reminder that what we call weather is really chemistry stretched across the planet's surface. Everywhere you look, or don't look, the invisible defines the visible. Paint glows because pigments scatter certain wavelengths. Glass is clear because photons find no reason to stop. The very blue of the sky is just air molecules scattering sunlight. Vision itself is chemistry. Photons striking retinal molecules in your eyes, triggering cascades of electrical impulses that your brain turns into landscapes, faces, and light. The act of seeing is the conversion of invisible energy into meaning. If you could shrink down to the size of molecules, the still world would dissolve. Air would thrum with motion, solids would blur with vibration, and liquids would pulse with endless exchange. What feels like rest? Your hand on a table, a cup of tea cooling, a breeze pausing, would instead reveal itself as a storm of collisions and oscillations. Stillness, as it turns out, is only a matter of scale. The beauty of chemistry is that it makes no distinction between the profound and the ordinary. The same principles that build stars also caramelize sugar. The same molecular interactions that power the brain also shape the scent of rain and the fizz of fermentation. Whether it happens in a cell, a kitchen, or a cloud, chemistry is simply nature's way of letting matter communicate. And yet, despite its ubiquity, it's easy to forget that all this motion surrounds us. The world feels solid, visible, and comprehensible, but beneath every surface there's constant flux, atoms binding, breaking, and binding again. We live inside a masterpiece of invisible balance. Every drop of water, every breath of air, every spark of thought is a reminder that visibility is only the surface layer of existence. The next time you watch steam curl from a pot, or rain bead on a window, or sunlight scatter in a glass, take a moment to imagine the invisible patterns beneath. Molecules pushing and pulling, light bending and bouncing, matter reorganizing itself in silence. Everything you see, smell, or feel begins as something unseen. The world is a clear glass filled with unseen motion. Beneath its still surface, the chemistry of life goes on, patient, balanced, and endlessly active. And though most of it remains invisible, its presence is everywhere, weaving quietly through breath and storm alike, sustaining everything that moves and everything that waits. It's easy to forget how much of life depends on what can't be seen. The invisible has a way of blending into the background, its constancy so familiar that it becomes invisible twice over, first to the eye and then to attention. But from the air in your lungs to the light in your window, chemistry is always there, shaping the quiet order beneath the surface of everything. The unseen isn't absence, it's the framework holding the visible together. Every clear breath is a miracle of gases mixing perfectly in proportion. Every glass of water is a liquid lattice of molecules, flickering in and out of hydrogen bonds with exquisite precision. Every scent that drifts through a room, every wisp of cloud above the horizon, every bite of food browning in a pan, all of it depends on molecules whispering to one another in silence. What appears still is only a slow kind of motion. The table under your hand vibrates with atomic rhythm. The air that feels calm is a blur of collisions. Even your own body is a web of exchanges, electrons jumping, enzymes folding, protons drifting through invisible gradients. The quiet chemistry of the world doesn't rest. It just works so gracefully that you can't tell it's moving. There's something profoundly reassuring about that. The universe isn't held together by chaos or chance, but by a patient conversation among invisible things. Molecules meet, react, and separate, each obeying the same unspoken rules that have guided them since the first breath of air on Earth. Out of their constancy comes stability. Out of their motion comes life. When you breathe in, the oxygen entering your lungs was likely forged in a star billions of years ago. When you exhale, the carbon dioxide you release may one day feed a leaf, or dissolve into the ocean, or freeze into a distant cloud of ice. Chemistry is the grand recycler, turning invisible particles into patterns that outlast every life and every era. Even the boundaries between living and non-living blur under chemistry's lens. The spark that runs through a neuron is not so different from lightning across the sky. The energy in a heartbeat follows the same laws as that in a burning candle. The difference is only in scale and rhythm. The same reactions that glow in the sun's core also glow in the mitochondria of your cells, less violently, but with the same quiet purpose. Perhaps that's the secret of invisibility. It's not there to hide things, but to remind us of how seamlessly nature works. We don't see molecules reacting because we don't need to. Their order is so dependable that it doesn't require our supervision. A glass of water stays liquid not because it's simple, but because billions of hydrogen bonds continuously form and break with perfect timing. The sky remains breathable because reactive radicals, ozone and clouds keep balance without anyone directing them. The chemistry of the invisible is not chaotic, it's the calm heartbeat of the world. If the visible world is a play, the invisible is the stage crew. It's the light technician, the quiet hand behind the curtain, the steady pulse of logic that allows the spectacle to unfold. The best chemists at work tonight are probably the ones you can't see. Molecules and microbes, catalysts and currents, all keeping things tidy while you sleep. There's comfort in knowing that this quiet order continues no matter what. While you rest, oxygen still diffuses, dew still forms, enzymes still hum along in every living cell. Even in darkness, the chemistry of life continues its rhythm. You don't have to notice it for it to work. It asks for no attention, only trust. Invisibility often feels like a mystery, but it's really an expression of peace. The more stable a process becomes, the less it demands to be seen. That's true of atoms and of life itself. The unseen isn't something to fear or solve. It's the sign that things are working as they should. And so, as this exploration of invisible chemistry comes to a close, the hope is that the next time you drink water, breathe deeply, or catch the scent of rain, you'll sense the quiet choreography at play. Every simple act is part of something vast and elegant, molecules moving through time, reuniting and separating, creating balance in ways that never need an audience. The invisible makes life livable. It is the constant motion beneath stillness, the structure behind spontaneity, the gentle physics of comfort itself. Even the calm you feel at night owes something to chemistry. The soft exchange of neurotransmitters easing your mind, the rhythmic release of hormones reminding your body it's time to rest. The science of peace is written in molecules too. So breathe deeply, wherever you are. The air you're drawing in has circled the planet countless times. It has brushed over forests, crossed oceans, and passed through countless lungs before reaching you. Every breath is a reminder that invisibility connects all things. May your next one remind you, even air has a story.